Okay, so to start with, you already have seen in chapter 3 how to deal with Rankine cycles and how to modify them in order to enhance their efficiencies. One possibility to enhance the efficiency of Rankine cycle is what we call the regenerative Rankine cycle. What do we mean by this? So in a problem, I can give you, for example, the following figure. And I will explain for you the system. So what will happen here? In general, you are familiar with this part. You are familiar with this part, okay? You have the turbine, you have the condenser, you have the pump, and instead of this, you know how to deal with this part, so directly to the boiler. Okay. However, here in this cycle, we have a new modification. We are doing, if you want, the work output from the turbine is divided like in two stages. So one part will be taken to a what we call an open feed water heater, and we'll see what is the function of it. Okay. And one other part will undergo complete expansion until 0.7. So if I want to describe for you the system, I will tell you that we'll do a small modification on the conventional Rankine system. We'll have the flow rate at 0.5. Okay, so let us say we'll do the analysis per kilogram. Let us say I have 1 kilogram per second coming from the boiler. Okay, now instead of having this 1 kilogram per second completely expanded in the turbine, okay, in order to have a work output, I will do the following. I will divide the flow rate into two parts. And we'll see why when we do the analysis of this cycle. I will take Y kilogram per second to the open feed water heater, and we'll see what is the purpose. And the other fraction will be taken to the condenser. Okay, so what will happen then? What will happen is that this part, which is taken to the open feed water heater, will be mixed with the fluid getting outside from the first pump. So here we have two pumps instead of one. The first pump will belong to the normal, if you want, cycle. So after complete expansion here, we'll go into a condenser, and in the condenser, we'll have a Q out, okay? And then when we reach 0.1, the pump will increase the pressure. But why we have here two stages? Because what we will do, we will work with 3 different pressures instead of only 2. In the normal Rankine cycle, you just have the pressure at boiler level and the pressure at the condenser level. And you need just one pump to get you from 0.1 to the maximum pressure. Okay, so if I want to compare with the conventional cycle, this is the conventional cycle. This is the P max. Okay, this is P maximum, PM max, and this is P minimum. And I just have one pump that will allow me to go to pump my fluid from minimum pressure, to increase its pressure from P minimum to P maximum in one compression stage. Okay. However, here, what we did is we divided the pumping process into 2 parts because we want to introduce an intermediate pressure. Now, what is the purpose of introducing this intermediate pressure? What we want to do here is to reduce, if you want, the heat input at the boiler level. Why? Because you know that at the boiler, you have a heat input. Okay. So in this case, when you consider the heat input, you will try to minimize it, because if you can minimize Q input, then you will increase the efficiency of your cycle. Okay, because we know that the efficiency is minus Q out over Q in. Okay, so one possibility to enhance the efficiency is to reduce the value of Qn. And to do this, we can increase the temperature at inlet of the boiler. Okay, so if you can, by doing this process, you will increase the average temperature at which you have heat transfer in your boiler, which will reduce the consumption of heat at boiler level. Because if you don't use this process, let's say, okay, you will go directly from this point to this one, then the amount of heat, if you compare the two cases, you will save this part of heat, okay, because you will heat from point 4 now instead of heating from this point here. So this area will correspond to the savings you will do, and by doing these savings in Qn, you will increase your efficiency. Of course, you can tell me, but Q output will also be reduced. It's true. Why? Because in the conventional Rankine cycle, you will expend the full fluid from this 0.5 to 7, while here you will just expend the whole part from 5 to 6, while only 1 minus y will be expanded from 6 to 7. So it's true that Q out is also reduced, but if you do the balance in overall, and we'll demonstrate it together now in a problem, in overall, you will increase the efficiency because you will gain more than you will lose. Okay. So this is the idea here. Now for the open feed water heater, it's a heat exchanger if you want. If I give you a heat exchanger and I tell you that it's completely insulated from the surrounding, how can you deal with it? How you can use it? If you want to write the energy equation here, what can you relate if you want? Do you have an idea how we can, by calculation, use the open feed water heater? Who can tell me? If I say that it's insulated from surroundings, so I can say that Q to the outer environment, okay? So I don't have loss of heat, okay? So I don't have Q lost. I don't have or Q gained. So sum of Q dot, if you want, lost plus gained is 0 because it's adiabatic. Okay, and I don't have a work rate. It's not a turbine, it's not a pump. So also sum of W dot is equal to 0. So I just have the flows of energy. I have a flow, two flows coming in. One flow is coming at enthalpy H6, and one flow is coming at H2, and the total mass flow rate is leaving at H3. So by just doing an energy balance, I can just put that m dot at 0.6 times enthalpy at 6 plus m dot at 0.2 times enthalpy at 0.2 equals to the total mass flow rate, m dot 3, which is the summation of m dot 6 and m dot 2, at H3. So I can use the energy balance here to find the fraction y, because look, what is, if I do the analysis per kilogram per second, m dot 6 is y. So I have m dot 6 times y, y times H6, okay, because y represents the mass flow rate fraction. So if I have in total 1 kilogram per second, y kilogram per second will be going through this pass, and 1 minus y will be going through the second pass. So plus 1 minus y times H2, because before going to the open feed water heater, it will go through the pump and will exit at state 2, equals to, so in total, if I sum y plus 1 minus y, it's 1. So it's 1 times H3. Knowing the different states, 3, 2, 6, 2, and 3, we'll be able to calculate the value of y. And for the other components, you are already familiar how to treat them, and we'll do this progressively. So you know that in the boiler, you have Qn. At the turbine level, you have W out. But here you should pay attention that W out is divided into two stages. From 5 to 6, okay, if you do your calculation, from 5 to 6, you have the first part of the flow rate will undergo only expansion from 5 to 6, while 1 minus y will undergo expansion from 5 to 7. So you should add the two outputs at the turbine level, okay? And you have Wn for pump 1 and Wn for pump 2. Okay, and we'll be able to calculate all of these parameters, and then we can calculate the efficiency of our cycle. So let us go over an example to see numerically how we can compute the fraction y, how we can assess the efficiency of the cycle, and how we can compare by calculation the efficiency to a conventional Rankine cycle. So here, for example, once I give you P maximum, P minimum, you can compare with a conventional Rankine system and see how the implementation of the open feed water heater will enhance the efficiency of your system. Any question on the operation before we start the problem? Okay, so let me start with a problem on this. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees and is condensed into the condenser at a pressure of 10 kilopascal. Some steam will leave the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. Determine the fraction of steam extracted from the turbine and the thermal efficiency of the cycle. So we need to find, if you want, what is the fraction of steam that is extracted to go into the second loop, and then we want to calculate the thermal efficiency of the system. So first, as usual, we draw the TS diagram. Here, if you want, we'll give you, because it's a new system for you, we give you the figure, we give you the following figure, we give you the physical explanation of the system, and you will draw the TS diagram, okay? So here, for example, if we consider first, let us start from point 1. So from point 1, we have, as we said, we have the flow is separated here. So here we have 1 minus y, and here we have y. Okay, and for point 1, we are just at the saturated liquid point, which of the pressure of the condenser. So we'll give you the condenser pressure. Since it's given, you can directly determine what is point 1, because point 1 is saturated at saturated liquid state. So from tables, then you can determine what is H of point 1. Now, once you know this state, knowing the intermediate pressure, you say that the first pump will allow us to pump our fluid from point 1 to point 2, and what is common between these 2 points is S, okay, because we are assuming isentropical compression. So you have S1 equals to S2. You know, of course, that once you know that it's a saturated liquid at a certain pressure, you can get from the thermodynamic tables what is H1, what is S1. Then you can deduce the value of S2. Also, in particular, the property that is important for you here, if you want to calculate W pump 1, who can tell me what is the variable that I need? Can calculate W pump 1, you can use the specific volume, okay, at point 1 times delta P. So times P2 minus P1. So also from the properties from thermodynamic tables at state 1, you will get H1, S1, and the specific volume V1. The specific volume V1 will allow you to calculate the work input at pump 1. Now, so we can characterize in this way point 1, point 2. Now, point 3 is the saturated liquid point at the intermediate pressure. So they will give us the intermediate pressure. At the intermediate pressure, we can go for saturated liquid to get at point 3. So also here, this is a saturated liquid point. But what is different is that 3 is at the intermediate pressure, while point 1 is at the minimal pressure. And from 3 to 4, you have the second pumping stage. So you can also say that point 4 is characterized by S3 equals to S4. And I get S3 from saturated liquid. So from saturated liquid at intermediate pressure, I can read H3, and I can read the value of S3 because I will need it for 0.4. And once I find S4, okay, I can also, knowing S4 and knowing the pressure, okay, knowing two characteristics, I can deduce what is H at 0.4. So from S4 and P4, I can deduce H at 0.4. And also I can determine, if you want, the power input from 3 to 4 in the same way I did for stage 1. So I can say that W pump at state 2 is equal to V2 times P4 minus P3. Now for 0.5, how can I characterize 0.5? What do I need? Who can tell me? So in general, okay, sometimes they will give you the temperature at the exit of the boiler. This is one way to specify this point. So you know the pressure, and knowing it's 0.5 is in the superheated state. If they give you the temperature here from thermodynamic tables, knowing the pressure and the temperature in superheated state, you can determine the enthalpy at 0.5. Okay, and then once we get H5 and S5, we know that once we go over the turbine, it's an isentropical process. We have S5 equal S6 equals to S7, but 6 will be the intersection with the intermediate pressure, while 0.7 will be the intersection with P minimum. So all points can be easily determined from our, already we have done a lot problems with conventional cases. We know how to deal with the thermodynamic tables and find H at different points. Now we'll focus in this problem on how to deal with our new component, which is the open feed water heater. Okay, so let us go step by step over the method. Okay, so first, going back to our given, we know the three pressures: the extreme, the maximum, minimum, and intermediate. And as we said, we know the inlet temperature at the turbine. So this is the temperature exiting the boiler. So as we mentioned, we needed to determine H at the superheated point. So now, having all of these, we'll proceed step by step. So as we mentioned, point 1 is a saturated liquid point. We go to the thermodynamic tables for the minimal pressure, which is 10 kilopascal. We find H1 and V1. And in case interpolation is needed, we do it. For state 2, we use that S1 is equal to S2, and the W pump for the first pump is V1 delta P. Then, if you want here, knowing that W pump is also H2 minus H1, once we calculate the value of W pump in, okay, we can use it to find H2. Because if we don't, 0.2 is in the saturated liquid zone. So this is another method to get H2. Instead of having, if you don't have the table of saturated liquid zone, we can use this one we have just, if you want, sometimes the saturated liquid at this level, saturated liquid. But if you have supercooled, so point 2 is in the supercooled region. If we don't have the tables for supercooled regions, or this point is not figuring out in these tables, we can use another method to calculate H2, because H2 minus H1 is simply equal to W pump. And since we know W pump from V delta P, then we can calculate H2 without having a table for supercooled region. Okay. So we calculate H2 based on H1 plus W pump 1. Now, next step will be to go to point 3. For point 3, as we mentioned, it's the saturated liquid point for the intermediate pressure. So we can write the specific volume, and we can read the value of H3. Then for point 4, we use the value that S3 is equal to S4, and we have the maximum pressure. And then similarly, as we did for pump 1, for pump 2, we have W equal to V delta P, and we have H4 equals to H3 plus W pump 2. So until here, it's exactly same procedure of calculation in normal Rankine cycle. Now, for point 5, as we mentioned, we use the superheated temperature. So we go to superheated tables and we determine H5 and S5. Then by saying that we have an isentropical process in the turbine, we can calculate what is, and using S5 equal to S6, we can, knowing the intermediate pressure, we can calculate H6. Please pay attention here. As usual, here you have two possibilities. You have possibilities that the point, in general, for Rankine cycle, the conventional one, the point will always follow within the phase of change of phase zone. Okay, and we need then to determine for point 7 what is the fraction of vapor and what is the fraction of liquid. However, for point 6 here, it might be, in general, it will be in the superheated region. Anyway, you can verify this from the table. So when you have a certain pressure, you can determine this, the temperature, the critical temperature. If you are above it, then you are in the superheated region. Okay, so 4.6, you will be in the superheated region, knowing the value of pressure and knowing S6 from thermodynamic, because it's equal to S5. From thermodynamic tables, you can deduce what is the value of H and what is the corresponding temperature. However, for point 7, as we mentioned, so you should find the fraction of vapor, which is between 0 and 1. But as usual, it will be closer to 1. So you can use then, knowing that S5 is equal as 7, and knowing the value of SFG from thermodynamic tables at the minimal pressure, you can compute the percentage of vapor you have as S7 minus SF over SFG, where SF is the value of S at saturated liquid, and SFG is the difference between SG and SF. So this is just, if you want the formula to get the percentage of vapor at your point 7. Once you get this percentage, then you are ready to calculate the enthalpy at point 7 as HF plus the X, which is the fraction of vapor, times HFG, which is HG minus HF. So now we have all enthalpies. We can move to calculation for our efficiency. Okay, before getting to efficiency, we still need to know what is the fraction of mass flow rate that will go through the feed water heater, and what is the portions that will undergo a complete expansion in the turbine. To do this, as we mentioned, what is the new thing in this problem is the application of the energy balance for the feed water heater. And as we said, because it's isolated from surrounding, so it's well insulated, we can consider that Q dot is 0. Because it doesn't involve any work interactions with surroundings, we have W dot 0. So we just can write that summation of energy flow getting in equals to summation of energy flows getting out. And as we mentioned here, we have two inlets, because one is coming from the fluid leaving the turbine at an early stage, and another one is coming from, as we said, it will undergo complete expansion in the turbine, and then will go through the condenser before being, so as you can see in the figure here, if you go back to the figure, this is the two flow rates we are talking about. Okay, so one will undergo complete expansion in the turbine, then will go through the condenser, then will enter the pump one to be compressed to state 2 before entering into the open feed water heater. So this is 1 minus y, which is, if you want the mass flow rate in kilogram per second, if we consider that we have a total mass flow rate of 1 kilogram per second in our system. So 1 minus y will go through this loop, while y will go directly to the open feed water heater, and then it will be extracted at a pressure that is an intermediate pressure. We said that the purpose of doing this is to facilitate, to reduce the heat Qn in the boiler, because this will increase a lot the efficiency of the system. Okay, so now if we want to write the energy balance as we did together before, we just need enthalpies of 0.6, 0.2, and 0.3, and we already found the enthalpies at these points. So we just have to apply the energy balance, which is, as we mentioned before, y times h6 plus 1 minus y times h2 equals to h3. Okay, so by applying this, the only unknown is y. You can find then what is the value of the fraction y. Okay, so this is why we can write y as h3 minus h2 over h6 minus h2. And then we get the corresponding fraction. Once we have y fraction, then we'll be ready to calculate Q input, Q output, and determine the efficiency. Let us do a small analysis on Q in and Q out. If we go to our cycle,